with that in my mind, I could probably take it slower and explain better. All right? Okay. So before we go into 7.2, there is one special case I like to cover. It's related to 7.1, but connecting to 7.2. That is for a distribution problem, a special type, where the connection between an origin and its destination are like extreme cases. Either there's no connection, no route could carry you through, or there's no limit of capacity, meaning the capacity, K here, takes either 0 or infinite value. Is that clear? So that's a bit like extreme, and it's a bit simpler in a way. Okay, let's say special. So I will talk about this special case. Okay, so special case meaning the capacity Kij will take value only from two possibilities. One is 0 and one is infinity. Okay, where infinity means unlimited, of course, unlimited capacity. Okay, and the 0 means there's no connection, right? So 0 means these two places are not linked, that I cannot ship through. Okay, so we'll go through 3 examples, and also to show you some example where you don't have feasible solutions. Okay, there's not a schedule that will satisfy all the demand. And in that case, I will show you how to identify the cell where you get stuck. That information is needed in the algorithm in 7.2 that we will talk about later. All right? So, and it was a step in the homework problem, but I told you can skip it, and now you will know. Okay. So let's take 3 examples. And to fix the idea, I'll just make the example small so it's easier to handle. So I'll have 2 origins, and I will have 3 destinations. Is that okay? I cannot make it smaller. If it's 1 origin, then you're finished, right? So at least make 2 origins. So origin 1, O1, O2, and I cut into 3 destinations. So D1, D2, and D3. Okay. So what I will put inside here is this situation, either infinity or 0. So I'll put infinity, 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 0, infinity, 0. And that's the demand, 20, 25, 35, and here's the supply, 30 and 50. Okay, you can easily check, verify that 30 plus 50, the total supply is 80, which is exactly the total demand. So if you shall find a feasible schedule, then there shall be no surplus, there shall be no unmet demand. Everything will be distributed, right? Okay, they exactly match. Okay, let's follow the algorithm that we introduced last time and see if I will manage to find a feasible solution. So you don't need to worry about the upper bound caused by the capacity now because it's infinite. So when you carry through the algorithm, all you need to check is the demand and the supply. Is that right? Take the minimum between those two, whatever it allows you. So could you tell me now, what would I put here as the first iteration? 20, 30, I take the minimum between these two, I get a 20. Is that clear? And then what would I do here? I would take minimum between 10 and 25. Is that right? So that gives me 10. Then I used up, and this 0 here. Is that clear? Okay, what can I put here? 0, because I already met my demand. And these are 0, so there's nothing I can put. Let's check. This is exactly used. And this one, I have surplus, 50 of them actually, quite a bit. Is that right? And this has met the demand, this has not. I have surplus 25, and I have surplus 35. Is it clear, the first iteration? Okay, this we had last time. Okay, now let's see if I can adjust. Let's take destination number 2. Let's see if I can meet the demand here. Oh, it should be 15. Sorry, 25 minus 10. Sorry. Will it be possible for me to ship 15 units more here? If I want to do that, and I see that I have all these surpluses which can only go out from column 1. Is that right? If I increase this by 15, can I decrease this by 15? Yes, it's 20, right? And then I can increase this by 15. I can get rid of that unmet demand. Is it clear? Those simple passes you see right away. So I see that I can meet this demand by increase this to 25, by decrease this down to 5, and by shipping 15 units more from O2. So this is that. Now I need to deal with the other one, the column 3. Let's see. So from column 3, the only place I can ship in would be here. I can ship in something here, and I could reduce something here and then increase something here by shipping out from O2. Do we see that? So that path would give me 5 units because I cannot ship more than 5 units out. So let's do that. So I will ship 5 units into this by making this down to 0 and by increase this to 20. Now I should have made that column a bit bigger. Okay. So then this unmet demand goes down to 30. Is that right? Should I draw this a bit bigger? Okay. Okay. Now, can I increase it further? Because you know you only have surplus here. The only place you could ship more will be in this cell if you start your labeling. This is R2, you start. R2 will be labeled in first column here. Is that right? Only this location. So once you're in this location, and if you make this bigger, you have to make something smaller to balance. Do I have any non-zero entrance? No. This is 0. If I make this bigger, I will have to make this negative to meet the demand, right? Then I'm stuck. I can't do it anymore. That's where you find out it's not feasible, right? So let's write out. So I'm stuck. Where am I stuck at? I'm stuck at this cell. If I want to ship more here, it doesn't allow me. Okay, so stuck at row equals 2, column equals 1. So this is the location where you get stuck. Okay, so this information is important in the next algorithm, right? So then you conclude it's not feasible. Is it clear? How to find it's not feasible and how to find this, because I need that number, all right? That column and the row index will be useful. Okay, so let's take another example. I want to show you that this could have multiple indices, not only just one location. Could be multiple places it gets stuck. Okay, so let's take another example. Let's see. Draw a similar length table here. Okay, so infinite. Wait a second. No, that's the new table is not. 0, infinite, 20, infinite, infinite, 25, infinite, 0, 35, and 30, and 50. Is it clear? So I have these 1, 2, 3, 4, these 4 places, there's connection between the origin and the destination, while the other 2 is not connected. Okay, so let's try to solve this one. Okay, let's follow this. Do the first row first, nothing here, and here 25, 30, I put 25, and then there's only 5 units left, I put 5 here. And for the second one, 20, I can ship 20, but then this gives me 0 because it's all done, and that's 0 because it's not linked. Okay, so this is all spent, and here I spent 20, I have surplus, and this is 20, this is 25, they are all met, and this is not met with the 30 units unmet demand. Are we okay for small problems? Can we set this up? For large ones, you really should use a computer software because it will drive the human head crazy. Okay, can't do that. Okay, now let's take a look at it and see, is there any path that I could use to probably adjust a little bit? Anybody spot any path? I want to ship more things into column 3. The only possible location was here, right? I could increase this a bit, right? If I increase this, then I'll be forced to decrease that one. And then if I decrease that, I will be forced to increase this, which is possible. So what's the maximum amount I can ship using this path? So this can be decreased by 25 units. That's set the limit. Is that right? So I can add 25 more units here. So let's say add 25 units. This gives me 30. And then this 25 unit is all taken away. And I put 25 units here. Is that OK? So which means I still have 5 units left, unmet. And I still have a 5 unit surplus here. OK, now let's check. How can we further adjust? So you start from the surplus, and you see that where could I increase, try to ship those 5 units remaining out? I could ship through here, because I could increase this. So R2 will be pointing in the column 1. And I could also ship here. R2 will be here. Is that right? If I increase this, I'll have to decrease this. Can I do it? No, I'm stuck. How about here? If I increase this, I will have to decrease that. Can I do it? No. So I'm stuck in 2 different locations. If that happens, you collect both. Okay, so stuck at, so R equals 2. That's the second row. But for the column, I actually have 2 locations, 1 and 2. Both of them makes me stuck, and I just cannot go at all. Is that clear, how to find these indices? And then you conclude that this is, again, not feasible. Okay, and this information we would need, okay, the indices. Okay, too depressing. Let's get an example that actually I can find a solution. So the last one. Okay, 1, 2, 3. Okay, so I have 0 here, infinite here, 20, 0, infinite, 25, infinite, infinite, 35, and 30, and 50. So as you might have noticed, these 3 examples, they all have the same supply and same demand. I'm just trying to find a feasible solution by just saying which of which is connected. Is that right? Okay. It will be, it's my sneaky way of sneaking it in, and you'll see why. Okay, so let's see how we can solve this problem. Is it possible to solve it? So look at the first row. Nothing, nothing. What can I put here? In this spot? 30. Okay, and then for the second row, what do I put here? This is the first one. I put 20, right? Because I have, and then this I need to meet the demand by 25. And then for the last one, I see I have 5 units left to ship there. Is that right? And now you see this is a simple example. You see there's no surplus and all the demands are met. Okay, so that means we have a feasible solution. So let's put the 0 there. So what is on the right is your feasible schedule. So I have found a feasible schedule. Okay, so some problem you can find and some you cannot. So is it clear how to do this? Any questions? Yeah?
Is it possible that when you rearrange and try to change where things are that it'll work out? Or will it have to be the first time?
Once you are stuck, you are stuck. That means it's not feasible.
Right, but is it possible that you have to move things around and it still could be feasible? Because
There's no way.
No.
If it's stuck, you mean I did not move 25 units and do it in the other way, you will still get stuck. If the problem is not feasible, it's not feasible. Which means the set of all feasible solutions for this problem is empty. So no matter from which angle you try to look for it, you will not find it. Do you find a feasible solution for this problem?
No, but would it be possible in,
Which example?
well, none of them? Because
Okay.
in these two, we tried to move things around, and both of them were not feasible. And in that one, we didn't have to move anything around if it was feasible. Would it be possible to move things around and make it feasible?
Oh, that question. Of course.
Okay.
Of course. Sorry, I misunderstood you. Of course. Yeah. We are really lucky that first shot is good, but we have seen in the class last time some problems, the initial guess was not good. We have to iterate quite a few rounds and we find a feasible solution, right? Right? That was your question, right? Yeah. Okay, so now let me don't take too much time. So is it clear how each of these steps is being done? Because this will be part of the next example. I will just cheat and use this, all right? Okay, now go to chapter 7.2. We really talk about transportation problem. Okay. So, okay, now we're talking about transportation problem. We're not talking about distribution problem here. And we need to introduce this new set of data. We call it Cij. That will be the cost to the price, right? So unit price, cost is actually a price, okay, to ship from origin I to destination J. So we have seen this. We are familiar with the transportation problem. So let's form the transportation problem. So we want to do a minimization problem. Minimize the total cost. Is that right? So how do I form the total cost? So the cost, the price is Cij. If I ship Xij unit, then the cost to ship the things from OI to DJ will be that. But then I need to sum all of them up. Is that right? Because I have a minimize. Let me write minimize. I have to do the double summation. I need to sum over all i's from 1 to m and sum over all j's from 1 to m. Okay? You add all of these numbers up. Okay? So that's that. And then subject to. And I have constraints. So we're looking at one special case. I will comment on that while we do that. That is the total amount of supply exactly equals the total amount of demand. That is everything must be exactly shipped. All the demands are exactly met. Is that clear? That's the one we'll be looking at. So I will have constraints with equal signs. So if I add up all xij, running j from 1 to n, so the supply at ai will exactly be used up or shipped out, going through all locations of the origin. And if I sum up through I, for each j, that means for the warehouse j, the demand is exactly met. Is it okay? And that goes through all the warehouses. Is it okay? And then, of course, these are non-negative for all ij in discussion. Do we remember forming up these problem? Okay. And then remember I said we made an assumption that the total amount of supply equals the total amount of demand. They exactly equal each other. Okay? Okay, so let's go into this method of solving this. So the method goes through actually the dual problem. It's called Primal Dual algorithm. It's a pretty lengthy algorithm. I thought about writing it down first and then go to an example and point out what you do in each step. But then I decided to do the other way. That is, we take an example, and then every step I write down the algorithm and then apply it to the example so you see what it means at every step of the algorithm. Is that okay? Okay. So here you would use the dual problem. So I need to form the dual. So for the dual problem, I need to introduce new variables. One new variables for each constraint that I have here. Is that right? And I have two sets of constraints. The first set comes from the supply, and the second set comes from the demand. Here there are m equations. Here there are n equations. So I'm going to label my variable like this. So ui, and then I from 1 to m, these will correspond to the first m constraint. Is that clear? So corresponds to first m constraints. Okay, and then I introduce another set of variable for the lower part. So j n, so they'll be correspond to the second or last n constraint. Is it clear what that is? Okay, so we're all familiar with the setting up the dual. So let's set up the dual problem. So the minimization problem is changed into maximizing. Is that right? Do we remember forming up the dual? You multiply each equation by ui, and then you add them up vertically. Is that right? And then the cost function will be added up vertically, the constant part here. And then each xij will be added up, and then you will have a constraint bounded by the coefficient there. We remember the dual? Okay. So I will be maximizing. Let's see. I will be adding up all ai times ui, I from 1 to m, plus summing over. The second part will be vj, j from 1 to m. That will be my new cost, right? Minimizing change to maximizing. Okay? So subject to, let's write down the constraints. So what are the constraints? Constraints will be this matrix actually, and if you write it out, So the total number of unknown here is very big, is m times n, and I have only m plus n constraints. So if you look at the coefficient of xij, xij appears once here in this computation with coefficient 1, and here also with coefficient 1. And then if you look at that one that goes up to the, what is it called, the objective function, that corresponds to the one with coefficient Cij. Is that right? So that gives you the constraint. So the constraint will be ui, because that's the equation ui, plus, and this will be the equation which we set vj as the variable. Is that right? Okay. And then it's maximizing, so this must less than equal to the coefficient here, so Cij. Is that clear? Okay, that's just to write up these constraints. Okay, and of course ui and vj, they come from constraints with equal sign. So what should that be? Are they restricted or not? Unrestricted. Is that right? So these will be all unrestricted. They could take positive or negative sign. It doesn't matter. Okay? And then these holds for you run through all the indices of I, and you run through all the indices of j. And that's the dual. Okay? Okay. So so don't worry, we actually never really needed to write out the dual, because we just have that problem in the back of our mind, and then we try to solve it, keeping in mind that these constraints are there. Okay? So I will go through the whole thing, taking an example. Okay? So I'll put the example here, and I will try to solve it. So I'll make a small example, 2 times 3. So let me give you the table, the data. Okay, so I have 2 origins, O1, O2. I have 3 destinations, D1, D2, and D3. Let's put the number in, 3, 5, 7, 4, 7, 11, 20, 25, 35, 30, and 50. Okay, so what I have outside here is the supply in each warehouse, and what I have down here are the demand for each destination. And what is in the middle of this table here is actually the cost, those Cij. That's the set of coefficients here. So now we are doing a optimization problem, not the distribution problem. Is it clear? In there, they're not K's, okay? They're the C's. K is the capacity. Now we don't talk about capacity for this setting, okay? It will come as part of the step, but it's not the problem. All right. And we can check 30 plus 50 is 80, and then add these up, you get 80. So everything must be distributed. All the demand must be met. Okay. Okay, so I will write each step down in the algorithm and then apply it to this problem. Okay, so let's look at. So first step in my primal dual algorithm will be, so I will attempt to construct a solution to the dual. The solution will satisfy the constraint here, but probably do not maximize the objective function. But as a first guess, okay, so construct an initial solution to the dual, okay, by doing the following. Okay, so So I will define the ui will simply equal minimum over all j of Cij. And I go through all the i's. Okay, let me write this down and then I'll explain. Then, once I have set that, and I compute the Vj is taken to be the minimum over I of Cij minus Vue, sorry, minus Ui. Okay, j from 1 to n. Okay, so I will do this. I will block it. If I block this, that's the algorithm. Okay, and then we apply it to the example. So what do we mean by that? Okay, so here in my example, how would I construct that u and v? So it's nicer probably to draw it in the graph. It makes it easier to see actually. 1, 2, 2, and 3. So it only depends on the coefficient of Cij, right? The rest does not matter to my problem. So I get 3 and the 5 and the 7 and then 4 and the 7 and 11. So I need to find I have 2 variables for u. I have u1 and u2, and I have 3 variables for v, v1, v2, v3, which I will put there. Okay? So what will be u1? Following the algorithm, it says I will be taking the minimum among all the numbers in the first row. Is that clear? Which gives me 3. That's a very simple step. Okay, and then what about u2? Well, that will be the minimum of the second row, which will be 4. So you're right. u1 is 3 and u2 is 4 right here. Okay? And then how do we compute the v? So v1, according to the algorithm, it says you should take the c and subtract the u. So take this column minus that column and look at the remaining and take the minimum. Is that clear? So this for v1 will be the minimum of 3 minus 3 and 4 minus 4, which will be 0. Okay? I mean, it takes longer time to write this out. You could see it right away. Is that right? So, okay, so v1 here is 0. Okay? So what will be v2? Would you see it quickly? 5 minus 3 is 2. 7 minus 4 is 3. What's the minimum between them? It's 2. Is that right? So minimum, okay, let me write out between 2 and 3. It gives me a 2. So v2 is 2. Okay. Will we be able to find v3 quickly? 7 minus 3, 4. 11 minus 4, 7. What do we get? v3 is 4. Is that clear? That's the initial guess. Okay. So by the way we guess this, we know now ui plus vj will be less than Cij. Is it clear? So by this we already know all the constraints for the dual will be satisfied. Less than or equal Cij, because that's how we constructed to make sure that happens. Okay. Okay, so this is the first step. And now I need to do a second step. Let me put it here. Step number 2. What do we do? Okay, I need to, based on that, I form now here comes the distribution problem. Okay. Using this UV into that, and to form the capacity. So Kij is defined as follows. it only takes value infinity or 0 for two different situations. It will be infinity if in this constraint I have equal sign. Okay? So if Cij equals ui plus vj. And if you have strictly less than equal sign, you put 0. Is that clear? Okay, so otherwise. Okay, so let me put the other numbers around. So I have 20, I have 25. Okay, let's don't put it. Okay, so this is the algorithm. Okay, that's what you do. You form a distribution problem like this. Okay, let's see here in our example how would I do it. Let's mark the capacity next to it because it's easy to check here. So here, how do you check? You look at 3 and look at this row and this column and this row. See, does 3 equals this plus that? If it does, then you set the k to be infinite. Is that clear? So 3 is 3 plus 0, so here I have infinite. And 5 is 3 plus 2, here I have infinite. And 7 is 3 plus 4, so I'll have infinite. Is that okay? And now 4 is 4, 0, add up, so 0. And 7, I have 2 plus 4, which is 6. So it's strictly less, right? So what do I put as capacity here? 0. Okay? And then 11, 4 plus 4, 8. Nope, doesn't match, 0. So now you have the capacity here. And then you have the following problem. So here, the problem, we will have the distribution problem as follows. So what do I have? Let's just sketch this up. Let's copy the number we did here. So infinite, 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 0, 0. And let's put the rest up. So I have a 30 here, a 50 here. That's where I want to send. 20, 25, 35. And that's the demand. So I'm facing this distribution problem. Okay, I formed it. So is it clear how this is formed? Okay. Now, here comes the third step. Okay, attempt to solve it. Okay, because we can try to solve it. It might have a solution or it might not. So then there's the discussion, right? So, and now here's the sneaky thing I did. Do you recognize this distribution problem? It's that one, isn't it? What you will have to do now at that step will be go through this and try to solve it. And you will find out that you get stuck. Is that right? Okay, so we see that from, so in principle you have to carry out the example 1. That part will be filled in here. That's your calculation, right? And we find out that it's not feasible. Okay, if it's not feasible, I need to find out the location, the indices. So I have R equals 2 and C equals 1. That's where I get stuck. And I need that. Okay, so I could write like stuck at that place. Okay. Right. So is it okay? I cheated out step 3 because we did it. Okay. Okay, now we go to step 4. Okay, it's not feasible, so I need to do something. So I need to find an iteration. I need to adjust these solution U1, U2, V1, V2, V3, and give a new guess and go through it again to see if I can solve it. Is that clear? Okay, so Now I will go through. This is the algorithm again. So I will define a new solution of ui and vj. Okay? So how do you do that? So we will do the following. We'll compute a number. We call it d. Okay, d is computed as the following. I'll do the minimum over, this is really complicated, so be very careful here. I shall be in the set of R, but J shall be not in the set of C. Okay? Pay attention here. And then I want to compute how much the constraint is not met at those places. Basically the slack. Okay? So Cij minus ui plus vj. I want to compute that amount and find the minimum of them. Is that okay? Okay. And once I have that, then I adjust the u. So as the following. So what do I adjust? Then the u I is changed. So you add that d to the ui. So I will have ui plus this amount of d. So you know this d will never be negative, okay? That's for sure. So plus, if the I is in the set R, okay? And you do nothing to this ui otherwise. Okay? And then for this vj, the next iteration, I will be changing it. So instead of adding, now I will be subtracting this amount. Okay? For all the j's in the set C, and then you do nothing otherwise. Okay? So this is just the algorithm. Let me block. That's my algorithm right now. Okay, let's see if I can apply this to my example. Let's continue from here. Okay, so for our example here, how would I compute the d? So d equals minimum over what? So let's figure out the set where I need to find the minimum first. I in R is 2. Is that right? And J not in C, going through all the other indices. So C is 1, so I have to choose the J between 2 and 3. Is that right? It could be 2 and 3. Okay. And then I need to compute kind of the slack there. Ui plus Vj. So yeah, so R equals 2, J is 2 and 3. So basically I need to check the slack in this and in this. Is that right? How much ui plus Vj does not meet Cij. So here I have 7 minus 2 plus 4. That will give me 1. And then here I have 11 minus 4 plus 4, which gives me 3. Is that right? So let me write down even with these numbers. So I will be computing the minimum. So let's say from I equals 2, j equals 2, that gives me 7 minus 4 plus 2. And the other one would be 11 minus 4 plus 4. Okay? And the minimum is 1. Is it okay? This d will always be a positive number. Okay? All right, and then we need to adjust. So go to the u. I see that only u2 needs to be adjusted. u2 now, I will have to add 1 unit to u2, right? So it will be 4 plus 1, it will be 5. Meaning this 4 here will actually be changed to 5. I need to change that one. Okay? And then for v, the only thing I need to change is V1, right? V1 will be subtracted 1 from it. So it's 0. You take away 1, it will be negative 1. Is it clear? So this guy now will be changed to negative 1. Okay. And once you have that, then you have to repeat the process. Now I have a new gas. Okay, so I need to go back to step 2 and go through everything one more time. Is that clear? Okay, so let's see. I'm back to step 2. What does step 2 say? Step 2 says form this problem, distribution problem. So let's see. Form a distribution problem. So for step 2 prime, at this iteration, what do I have? Let's put in the numbers. Let's see. Okay, so I have u equals 3 and u2 equals 5. Okay. And so V1 is negative 1. V2, V3 are not changed. Okay, you could do it on the same table, but by erasing the old result, but let's write a new one. So I have 3, 4, 20, 5, 7, 25, 7, 11, 35 with the 30 and 15. Okay. Let's build and find the links and put in the capacity K next to it. So what I'm putting now will be the capacity. Okay. So what should I put here? Does 3 equal to 3 minus 1? No. Then what do I put? Infinity or 0? 0, right? You only put infinity if they equal each other. If these two numbers add up, equal that, right? That gives you infinity. 3 plus 4, 7, infinity. 5 minus 1 is 4, infinity. 5 plus 2, 7, infinity. 5 plus 4 is not 0. Is it okay? Do you know how to fill in this infinity and 0? Is it clear? So this means I have the following distribution problem. If you really want me to write this out again, so I have 0, infinity. So that's the distribution problem. Okay, infinity, 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 0, 30, 50, 20, 25, and 35. So that is to form that. And then I will have to try to solve it. Step 3 says attempt to solve. Okay, so as you are expecting, we just did it here, right? We solved it. We try to solve it in example 2. So solve. We see that from example 2, we found out that this is actually not feasible. And where do we get stuck? Stuck at R equals 2 and C actually both in column 1 and 2. Okay, it could carry multiple indices. For large systems, you could have multiple places with surplus, and it could all get stuck. So R could even have multiple indices. Okay, right. Okay, so that's step 3, and then and we need to go to step 4 and redefine. So that means it doesn't work. I still have to go through the thing. So step 4, let's compute the D again. In this case, so what will we be taking minimum over? Minimum over I equals R, that is 2, and J not equals C. C is 1 and 2. The only number that's not in it is 3. Is that right? So I actually have just one cell to check for the slack. What is the slack of that, right? So it's just this one I need to check. Is that right? So what I will have to do is 11 minus 5 plus 4, which is 2. Is it all clear, every step what I'm doing and how you get these numbers? If there's anything unclear, stop me and ask. Is that right? Because I have only one cell, then I just calculate that number. The minimum is that number. Now I will add, I will change my U now. So U is 2. So U2 will be further changed. I will add 2 units on U2. So I will have 5 plus 2, which will be 7. And then for V, I will have to change 2 of them. V1 and V2 will both be changed. So I have V1 double prime. It will be, it's already -1 minus 2, so it's -3. And V2, at that stage, I will get 2 minus 2, which is 0. So I have a new guess of the solution to the dual problem. Is that right? Okay. And then what do we have to do? Well, we have to repeat again. Repeat from step 2. Because we have to find a solution. This is still not feasible. Okay, let's go to step 2 and see if we get lucky. What do you think? Will we get lucky this round? So step 2, second run iteration. Okay, so let's set the table. I have, this is 3, this is 7. That's the new U. And the V will be -3 and 0 and 4. And let me fill in 3 and 4 and 5 and 7, 7, 11. I only need this part. Don't get the rest. Let's just find the links first. And then we form the distribution problem. So let's assign capacity. 3 does not equal to that. 5 does not equal to that. 7 equals to 3 plus 4. 4 equals that. And 7 equals that. 11 is 7 plus 4. So we assign the capacity. Is it clear? And now you have a distribution problem. So distribution problem. Okay, so we can, if you want, you can write it out. Or if you put everything in one table, then probably you don't need to write out. So I have 0, 0, 0. Oh, no, 0, infinity, infinity, linked, linked, linked. And 30, 50, 20, 25, and 35. So that's the distribution problem you will need to solve at this step. Okay? So, and you see that I actually prepared it as an example earlier. That's example 3. Is that right? Okay, so we have a feasible solution from example 3, which is listed there. Let's list it here in a table. Let's list a table like this. So in each cell of the table, I will put in the cost, Cij, and then right next to it is the schedule that we found is feasible. Okay. Let's write it out. So what would I have if I just do this? let's just put the schedule. So the cost is 3 and the 4, and the schedule that was feasible was 0, 20, and let me put in the C's first. 5, 7, 7, 11, and the schedule was 0, 25, and 30, and 5. So here are the costs, and then on the right, this is the schedule. And we found out that it's feasible. Okay, so it's a new scenario, right? Earlier, we were all finding not feasible solutions, and now we finally found one that's feasible. Okay, and then we need to know what to do here. All right. So this is the ending of your algorithm. Now you can terminate. So once you have found a solution, then good news, you're done. Okay, so let me write down. If there is a feasible solution for the dual, not the dual, for this distribution problem. Is it clear? Let me don't write. It's very clear what we're doing. We're forming a distribution problem and try to solve it. Okay. If you shall find a feasible solution, okay, it might not be unique. Okay. As long as you find one, then any of them, any of such solution is an optimal one. So it will be a minimal cost schedule. Okay. This is a claim. We didn't prove it, right? We just accepted. Okay, the algorithm is telling me that will be the one. If you're curious, you want to take a closer look at what it's doing and why it gives you the optimal, feel free to do that. It goes into the duality theorem. It's actually solving the optimal problem for the dual in this setting. And then it gives you the optimal solution for the original problem. Okay? We'll not go into that. No time. Semester is ending. Okay, so, and this will be the schedule for the original transportation problem. Okay, so let me block that. That's also part of the algorithm. So this is what you do if you solve it. Good news, you're done. That's all you needed to find out. Okay. And then the last step to do, probably the problem would be asking you what is the minimal cost, right? So final step, you might want to compute the minimal cost. Okay. Well, if you write everything down like this in this table, then the cost is very simple to compute because it's just the sum over Cij times Xij, summing over I and j, all of it. Is that right? So you multiply those pair of numbers and then add them all up. Is that clear? So you will have 0 plus 0 plus 7 times 3, that's 210, plus 80, plus, what's 7 times 25? That's 7 quarters, a quarter less than $2, right? 11, 5, 55. Okay, add this up. Okay, I did it in advance, so 520. And then you finish it. So Now, except this, beside the step that we didn't really prove this claim here, is it clear how the algorithm is working out? There'll be one homework problem for you to go through this for one example, and you get bonus points for that. Do you want to try it? That problem is not 2 by 3, it's 3 by 4. If you feel this is insufficient, read the book is very brave and give you 2 more examples and 3 by 4, 4 by 5. Okay? Let's say in particular, you can read the example in the book, the next one, 7.2.3. Okay? And it might not use exactly the same notation that I use because I prefer to write out the distribution problem to make it clear. The book just embedded with this big table and cross out and keep marking. But if you know what it's doing, if the algorithm is clear for you, you can read through it, hopefully not being too much bothered by slight difference in notation. Is that okay? So, okay, so any questions? Anywhere that is not clear? Is this crystal clear? Okay, so I want to tell you that, okay, so for the final exam, this whole algorithm here will not be on the exam. It's too big. There's no way I could test you on this. That's why I give you the homework for you to practice. But problem of this type, and you see it can be done in a couple of minutes. So these will be subject to final exams. Is that clear? I'm saying too much. Yeah.
So is it more like from 7.1?
7.1 is long, where you actually have capacities that adjust is more work. I would give you just infinite or 0. So you feel free to adjust.
But we won't have to do the whole, like finding...
No.
Okay.
Just solve it. If you find a schedule, tell me. If it's not solvable, you tell me where you get stuck. Give me the reason why it's not solvable. You say right here, I'm stuck, I can't move anymore, and there's still unmet demand, so it's not feasible. Something like that. Is that possible? So maybe 3 times 4. 2 times 3 is teeny weeny. So there are problems in the textbook, which is assigned for the next homework, that you will have a couple of these problems to practice and one of this big problem to go through. All right? Okay. So I have 5 minutes. Let me make one comment, which I could probably just talk and maybe we can understand it. So this algorithm, remember when I set up, we talked about all the constraints, we set them to be equal, right? So just one little discussion. So remember, for the problem we have here, we had in this problem, summation over all I equals summation over all bj. So your supply exactly equals demand, which leads you to all equal sign in the constraint. Is that right? Because they have to be exactly met. So that doesn't sound very general, does it? What if I have more supply than demand? Can I still use this algorithm? So here's the question. What if I have the other situation that, okay, this will possibly give me some feasible solution. I have my supply, and it's strictly bigger than my demand. Then this could lead to inequality sign in the constraints. I mean, theoretically speaking, is that right? Because I will have slack, I will have surpluses, some warehouses that will not be shipped where all the demands could already be met. You agree? So, okay, any suggestions? What do you think one should do? So, I am that type of guy that is, if the hammer is the only tool I have, and now turn all my problems into a nail. Can we turn this into that nail that we know how to hammer? Any suggestions? I still want to use the setting, that long algorithm that we just talked about, by doing some adjustment here, by seeing it in a different way. Any suggestion? Hmm? Uh-huh. That's the way to go. It's in the right direction. Think one step further. I want to put it in the same setting. That is, I have original locations, I have destinations. But then, after I shipped all to the destination, I will have some surplus left. Can I think that I have an imaginary destination where all the surplus exactly went there? Do we agree? Then I add one more destination. Then for the new problem, I will have equal sign everywhere. Is that simple? Do we see that? Okay, so one imaginary destination. So D destination orders to N. So let's say Dn plus 1 to store or surplus. Okay? And then it turns into that nail, then I can hammer. Is that okay? And we're not going into examples into that. That's just rewrite it, and then you carry out the same algorithm. All right. Okay, any questions? I think that's all I have to teach you, and on Thursday we'll do a review. So could you think about it and give me feedback so the review will be more effective? Is that okay? Yeah, question?
When will you open up the Dropbox for the bonus homework?
I will open today.
Okay.
Yeah.
I don't want to have to remember.
Yes,
Okay.
do the bonus today when you remember everything. After you review the whole course, it'll be gone. Okay. All right, see you on Thursday.